Welcome everybody to the online classroom here. We are Sierra Mountain Centre based in Bishop here. I've been running Sierra Mountain Centre since mid-90s, been living in this area since 1980 or so. If anybody thinks I have an accent, no, I really don't, you guys do. But originally I'm from New Zealand. Been living here, as I said, since 1980. I came to the US climbing, traveling, doing a vagabond life, ended up working at Rock Creek Lodge just up the road here for 6-7 years. For the winter, snowed in, and that's where I started to learn about avalanche, activity, safety, and evaluation. And I've gone on since then. Been teaching programs since probably the 1990s. So I've been around for a while. However, I'm certainly not going to say that I know everything by any means. And every time, as I'll emphasize as we go along, every time you go out in the snow, you should learn something. It mightn't be what you went out to learn, but you should learn something. If you're not keeping your eyes, your ears open. As I said, we are Sierra Mountain Centre in Bishop. This is our wonderful office manager, program director, Emma, and Emma was out there somewhere just to check in. A lot of you might have already spoken with her on the phone. We got snow, but it's been a while. I went up to Tioga Pass yesterday, and this is what it looked like up there. There is snow. We're still hoping that we can do our next field session coming up in a week or so. Up at Tioga Pass, Emma and I have been talking about this. There is enough snow to make it work. The good thing about Tioga Pass is you get to look at some really good terrain up there that normally you wouldn't without at least a solid day of skiing. Looking here over Tioga Lake towards the pass. The lakes are solid frozen and it is just gorgeous up there at the moment. Ellery Lake here, glassy ice skating, if anybody's interested in getting the skates out. There were people up there skating, and I didn't go out to check thickness, but it looks pretty good, and it's clear. Along with the classroom session here, we do have the field session, and the two go together. People should by now be signing up or have signed up for the field session. If you can wait until later in the season, great. If you want to get everything dialed so you can start to head out and have some confidence in your decision making, doing an early season course, we're certainly able to get a lot done out there. We never know what we're going to get for snow. This is 3 years ago at Tom's place where we had snow early December all the way down to Tom's. So as far as the field sessions go, we want people to be adaptable because we want to go where the best snow is. And that might be Bishop area, it might be Rock Creek, it might be Mammoth. Mammoth definitely has the most snow, and that's something we'll talk about during the field days as to why Mammoth gets that much snow. There is snow at Minaret Vista at the moment. I'm hoping to get up there in the next few days and check it out and just see how much we actually have. I've been corresponding with our other instructors to see how they feel about things and what we're able to do. But the field sessions will be in the next integral part of the program. We're doing here a level 1 program that is an introduction to a risk management framework. When we're out there, we want to manage the risk. Now, there's risk in everything we do, whether it's skiing, climbing, driving a car, chewing a piece of steak, you can choke on that. But there's risk in everything. Our skiing is a recreational and voluntary activity, as opposed, you could argue it's different to driving a car in Los Angeles traffic to work, which a lot of people say isn't voluntary. But we're supposed to have fun, we're supposed to enjoy the environment, and we're supposed to come back safely. if we manage the risk, we make this a repeatable event. And that should be what all of us want, is a repeatable event. We can do this for day after day, year after year. No, I plan to be doing this when I get old, at least in my 40s. We want a system rather than a haphazard, no, well, I don't know, what do you think? And that's what we're aiming for here. So we do have the online session, and this is the link to it here. The online session is part of the whole process here. And Emma did put a list together for me for people who have started it and people who have completed it. I'm going to start, if this works, a little poll here. And how about people go ahead and click on an answer there. Tell me where you're at. Yes, no, partway through. 20 out of 20? You guys are good. Wow, I am impressed. That leaves 3 people. I know 2 of those who might check this out, but not necessary. So good job. I am impressed. So there's the results. So nice work, folks. This is a AIARE program. AIARE is American Institute for Avalanche Research and Education. This is the AIARE 1. A couple of years ago, both AIARE and the American Avalanche Association. The American Avalanche Association is sort of the top level. They come up with a number of outcomes they want from courses. That is disseminated down to a number of providers, of which AIARE is one. And then we are a provider for AIARE. As I said, a couple of years ago, the programs were redefined into a recreational track and a professional track. Here we are talking about the recreational track. And for the AIARE 1, we want people to learn a process, a means to apply decision making. Then get out, get experience. No, we're dealing with theory here, but Avalanche evaluation is a practical thing. You've got to be out there using it and gaining experience. Then after that, you can get into the AIARE 2, which is upping the level and coaching and applying what you learned at the level 1. Avalanche rescue, we cover that in the level 1 here, and that'll be part of the field session. However, it's not everything you need to know about avalanche rescue. So the avalanche rescue is split off as a separate course, and you can plug into that at any point. For the level 1, we want to give people the skills so that they can go out into the field with us and be able to deal should something ever go wrong. We recommend doing the full one-day rescue, which gets much more into group rescue strategies and things like that. And it's something that's good to do every 2 years. You can stop your education if you want at the AIARE 2, or you can move over to the professional track, going through a Pro 1 and a Pro 2. The Pro side is generally for people who are working in snow, avalanche forecasters, ski patrollers, guides, that type of thing there. So that's the division of the different courses. People often ask the difference between the level 1 recreational and the 2. These are some of the things summarized here. At the 1, you're more contributor. At the 2, you're much more of a facilitator. Level 1, you're identifying and recognizing different factors. At the 2, you're assessing and evaluating and managing the risk more rather than just being a participant communicating it. So that's the difference between the level 1 and the level 2. So today, we're currently in our intro here. Then we're going to go ahead and we'll look at what we'll call the avalanche problems of terrain, weather, snowpack, and ourselves. In the afternoon, we'll look at how we deal with those problems through preparation, planning, teamwork, writing, and debriefing. So that's the outline for today. When we get in the field, we'll run over companion rescue. We'll talk about terrain assessment. We'll talk about route selection, and we'll dig into the snow and see what's going on underneath the surface. The second day, we'd like to tour and put it all together, and we'll be throwing a lot more things at the participants saying, no, what do you think? What do you see here? That type of thing there. So, why are we doing all this stuff? Regrettably, people die in avalanche accidents every single year. And this is going up to 2021, over 70 years here. You can see the graph is climbing, there's up, there's downs. Obviously last year, would have been a down because of COVID. People weren't out there. Things can go down because of a dry snow year. Things will go up because there's more people out in the backcountry. So overall, the rate though is climbing for a number of different reasons, and we'll talk about that as we go along here. By activity here, we can see that backcountry tourers are the biggest group that is hit by avalanche fatalities. Snowmobilers are less. Climbers. Climbers unfortunately tend to be pretty oblivious about avalanche danger. Climbers are oblivious a lot of things, but particularly avalanche danger. Last year, let's see if that shows up for people. Accidents in North American mountaineering. Had a whole article or a series of reviews on climber involved accidents, particularly ice climbers, particularly mountaineers. So if you're a climber, during the presentation here, I'm going to focus more on the ski side, and I'll probably use the word skier because I'm a skier. That doesn't mean that I'm ignoring climbers, snowboarders, snowmobilers. I'll try and include those, but I'm skiing oriented here. Hikers, particularly in the spring, get killed by avalanches. And with more and more people on the PCT and the JMT and early season conditions, I wouldn't be surprised if we see more hiker fatalities. Inbounds. Ski Patrol does the best job they can on mitigating the danger. They're not infallible and things go wrong. And this here is the nightmare of every Ski Patrol director, is having inbounds accidents after they've done control work. But, oops, it happens. Ski patrollers, they die. They're out there all the time and they get in trouble with avalanches. After that, it drops motorists. People do get hit in cars. So it can span a variety of different people. Where avalanches occur. Again, we've got nearly 70 years of data here. And obviously there's that big flat area in the middle of the US where not much goes on, and we aren't there, luckily. Mountain states over here tend to get the majority of the accidents. So Colorado over here leads the pack. Utah. However, we've got a couple of sparsely populated states up here in Idaho, Montana, Wyoming, this area here. We'll talk about some of the why of that later as we go along. So keep that in mind. Over here, we've got California. We've got a lot of people in California, but relatively low compared to the mountain states. And we'll talk about the why there. Washington State is up there. Alaska, 166 there. So it's way up there as well. But we'll discuss that as we go along. Plug this into your thinking. Think about why some of these areas might have higher fatalities. Also keep it in mind, if you go from California over to Colorado, there's a lot more accidents there. The bottom line is we can't take what we learn in California and necessarily transfer it automatically to Colorado, and more on that later. By month, really the only month we don't get many fatalities is September. Obviously, they trail off in the summer. However, as you'd imagine, January, February, we get them. October, we can get avalanches. I know people in this area locally who have been hit by avalanches in October with the first snowfall. And I was anticipating we might see that during the early snowfall we had this year. It didn't really happen, but any time of the year we can get them. Most of the time over here, the accidents are related to climbers, not to backcountry users. Age group. So anybody out there in the 20 to 30 demographic? Oh, getting a little wave there from some people. Well, as we know, if you can survive through your teen years to about 30, you can probably survive a lot of things. And this just isn't related to skiing at all. However, this chart now does tend to be shifting, and it's moving upwards in that there is data that shows that older people are getting caught in avalanches more often than they should. That can be a reflection of changing demographics, where there are older people going out into the mountains more and more now than there ever used to be. Obviously, there's not that many below 10 out backcountry skiing, but there are some. It used to be there weren't that many people over 60 out there. Now there are. So this is getting bumped up. This is data from last year, where in the US, 37 people died in avalanches last year. So last year was a bad year for avalanches. Despite a lot of the mountains being closed down due to COVID during the winter. Again, this can be a reflection of just there being more people out there. So we've got to take statistics a little bit carefully when we look at them, but overall the trend is upwards. So that's some data on the statistics. Said that there's 5 different levels of learning. You guys are obviously beyond the bliss phase. If you're in the bliss, you'd be, down at the loony bean having a cup of coffee and thinking about what you're going to do for the day and unaware of things. Now, maybe you're in the terror phase. That's fine, but we don't want terror to stop us getting out there. What we found is that people often go through these avalanche courses and they come out at the other end and go, oh my God, I'm never going to go in the backcountry again. It's too damn scary. That's not what we want to do here. What we want to give you is an awareness of what can go wrong and also what can go right. No matter what, we've got to avoid the overconfidence phase. In a lot of arenas, overconfidence comes after about 7 years out there. And when we look at it, and we'll talk about this further along, 7 years isn't very long out there, but it's often, I used to fly paragliders a fair amount. There it was referred to as intermediate syndrome. Now, yeah, I've seen it all by now. I've been doing this for a long time. I've been doing this for 7 years. It's a long time. It doesn't matter what you're doing. As soon as you get overconfident, you're a danger to yourself and everybody around you. And it doesn't matter if you're running a chainsaw, driving a vehicle, whatever. We've got to avoid overconfidence. If we can get through the overconfidence phase, then we hopefully get to the expertise phase. And we all aspire to the wisdom phase. Unfortunately, most of us never get there. No, we've all been through the last year with COVID, year plus now it seems. We've learned a lot, and there's a lot of similarities between what we want to do with our avalanche risk management and with our COVID risk management. I'm still being careful. I'm not taking risks. I'm just being careful and aware. We had a stay-at-home order. That's the equivalent of staying away off the steeps. It might relate to our avalanche warning. It was a high danger rating. We've got something unseen. It is evolving, as we're seeing now. We can reduce our exposure, by not being around large groups or avoiding specific terrain. We can wear a mask, we can wear a beacon, we can educate ourselves. We can choose who we're interacting with, and we're always assessing and mitigating it. And I found for a lot of avalanche professionals, the COVID risk management hasn't been that difficult because we've been doing it for a long time with our avalanche risk management. People now who are starting out can maybe take it the other way. Take what you've learned from COVID risk management, put some of that into your avalanche risk management. As I said, we don't want people coming out of this afraid. What I'd rather see is everybody exhibit respect for the terrain and the environment we operate in. In other words, we're giving particular attention. So, do any of our millennials out there have a clue who this is? Anybody? Aretha Franklin? Respect. So, no, what we need is a little humility in the backcountry. No, unfortunately, we often don't have that as a species and as individuals. But if you're humble in the backcountry, you're probably going to survive a lot longer. What I'd like to do as we go along here, we're going to cover an awful lot of material. Some of it's going to be complex, some might now go over your head. When we do a refresher in the field, we'll be asking questions. And there's a lot to learn here about it, but I want to try and simplify it. We're going to talk about the avalanche danger, and we can get ratings from the Avalanche Center. It's going to vary from low to extreme. The bottom line here is as the danger goes higher, our terrain selection gets simpler and lower angle. As the danger goes lower, we can push it into complex, steeper terrain. It's not that difficult. We can always get out there and find something to ski, ride, board, climb. We just have to choose the right slope for the right day. And that's where the trick is. You can make it simple and you can live by rules. And we'll talk about this as we go along here. As our danger rating goes across here, the terrain that's open to us becomes more and more reduced. Now, even over here where we have a high or an extreme danger rating, we've still got a little bit of green. We can still go out and have a good day in the mountains. We mightn't be skiing steep, we mightn't be skiing deep, we mightn't be skiing what we headed out there to do, but we can find something to do. As the danger is lower, there's more and more terrain open to us there. So we can choose low angle terrain and still have a good day out there, even if the danger is high. So we'll be talking a lot about this as we go along, and we will come back to this graphic a couple of times. And this is taken from a Canadian system, and I'm starting to utilize that more, and we'll talk about it. But in reality, keep this in your mind, and this is all you really need to know. The more danger, the simpler terrain. The less danger, the more we can step it out. So that is the end there of the introduction. But we've got weather, snowpack, and terrain. What we're going to talk about now is snowpack, one of the arms of our, or sides of our triangle. So snowpack. All right, I'm turning things over to you guys here. Write down in the chat box as many words for snow as you can think of. No scientific terms, skier terms, boarder terms, climber terms. Go for it. Powder, nah. Sastrugi, there's a good word. Fluff, powder. Faceted, maybe we could call that a technical word. Crusted. Okay, ice, slough, lots of different words out there. Corn, there we go. Okay, so we've got lots of different words for snow. No, it's said that the Inupiat of the Arctic have 100 different words for snow. For them, it was the way that snow would perform under their sleds, how it was for the dogs, how it was to travel on. For us, it's often how we ski it, whether it gives us good skiing or not so good skiing. So think about the best snow day of your life. What was the snow like? What was the weather that led to that snow? Let's put it in the chat box there. Big cold storm, dry, fluffy snow. Yep. What else? Somebody's agreeing, Gabrielle. Light and dry, okay. Deep, okay. What was the weather that gave it deep? Probably a really persistent storm. So we're trying to link the weather that gives us good snow, and we'll also link that in a bit to weather that gives us avalanches. How about the worst snow that you've skied or boarded or ridden? What was the snow like? What was the weather that led to that? Put it in there for me. Mashed potatoes, okay. What gives us mashed potatoes? What type of weather? Ice, light storm, says Gabrielle, then heated, then it warmed up. Ice, okay. What gave us ice? Okay, what gives us ice there, Daniel? Paul says sunny, slush. Daniel says wet. What followed the wet? Yep. Yannick says warming during the day, freezing at night. So yep, warm, then freeze, then it's ice, then it's just hellacious to ski. So now snow falls to the ground at different times in different weather conditions. That's what gives us our snowpack. Oftentimes when we go out there, we see just a layer of snow. We've got to think about what's going on underneath the surface. And the snowpack reflects every storm that we've had. We're going to have layers that come from a storm. Then we have interfaces between the layers that reflect the conditions between those storms. Here we have a dust layer. This is snowpack in Utah. In Utah, this is very typical now of getting the dust layer. For avalanches, it's the layers with different characteristics that give us different potential layers of weakness that lead to avalanches. Let's define our avalanches as two different types. We can have a weak layer over a strong layer. That gives us what we'll call a loose snow avalanche. Then we can have a strong layer over a weak layer, and that gives us what we'll call our slab avalanche. So this is our first division of avalanches here. Loose snow, slab. And we'll talk more about those as we get into it. Our layers always change. Surface here, these are really nice bear tracks. At some point, all these surfaces are going to be buried. They're going to be an interface within the snowpack. We're going to say that there's two different types of change in the snowpack. We're going to call these direct weather effects and indirect weather effects. Direct weather effects are what happen at the surface. And somebody already brought that up previously. No, Yannick said warming during the day and freezing at night. That's what happens at the surface there. And that's going to reflect, as we talked about, as ice. Weather effects at the surface. Okay, in the chat box there, give me some things that are going to affect the snow at the surface. I'm thinking of 4. We've got wind, we got sun. What else? Rain, yep, rain, yep. Temperature, good job, guys. Got them all. Wind, temperature, solar radiation, sun, precipitation. Doesn't matter what that is. It's rain, it could be snow. a variety of things there. It's often a combination of those. So pretty much everything we see at the surface is going to be buried at some point and become our interface. So that's at the surface. Now we have changes that happen more deeply within the snowpack. And these are what we'll call our indirect weather effects. We're going to veer very slightly into snow science here. Very slightly. We don't have to go much into the science at all, but I just want to give folks an understanding of what factors drive change deep in the snowpack, because that affects the type of snow that we get. So there's going to be two different things that are going to affect our changes deep within the snowpack. And that's going to be primarily temperature and the amount of snow that we have. Let's take those and look a little more closely. Keep those two things in mind. Let's make a little bit of a graph here. Height of snow vertically, temperature along our other axis. The concept here is once we get snow cover on the ground, our ground is always at 0 degrees centigrade. No, we're working, this is science, we work in centigrade. We count to the base 10. It's a good thing. It's pretty handy to know. Those Euros really figured that out. Or if you want to, if you're American, 32 degrees Fahrenheit. You know, if we walk outside now, say when I was up at Tioga yesterday, the ground is frozen. I can go out, I kicked at the dirt, it's frozen solid. That's because it doesn't have any snow on top of it. Snow insulates. It holds air. It allows the ground to stay warm. The ground absorbs heat over the summer, and then it re-radiates it during the winter. If it doesn't have an insulating blanket of snow on top of it, it continues to radiate and cool. Once we get snow on top, it's a very good insulator. It insulates the ground, and the ground, once we have snow cover in our environment, if we go to the Arctic or the Antarctic, that might change. But our ground is at 0 degrees C, 32. We'll find that when we dig into the snowpack, the ground won't be frozen, and you know, a lot of life owes its existence to that fact. That's how plants and animals get through the winter. Voles, mice live at that interface where it isn't freezing. So our ground in our environment is at 0. Let's add 50 centimeters of snow. That much. There. Now next temperature we have to consider is our air temperature. And that's going to be whatever it is. I'm just going to pick a number here, -10. Again, we're working on that science centigrade. So our ground is 0, our air is at -10. If we wanted to sort of graph that, we end up with a gradient of like that, where we get a change of 10 degrees over 50 centimeters of distance. All right, let's change one thing here. Let's add more snow. Now we've got 200 centimeters. Wouldn't that be wonderful? Our ground is still at 0. Our air is still at -10. But now we end up with a different slope to our line there. We get less change of temperature over distance. Everybody got that? More change, less change. One thing to remember here, this is a very simplified explanation. I just want to introduce the concept here. This isn't what we actually get in real life, because I said air is a very good insulator, and it will tend to keep the temperatures that the snow originally fell at. So we will get these changes, but it may be over shorter distances, and we'll get more of a zigzag type line. But we're just trying to keep it simple, because our gradient there which one of these two slopes we have affects the type of snow that we get. We are going to go further here, and we have two different types of snow that we get on the ground. Remember, we're talking about snow on the ground. From the sky, we get crystals. Those land on the ground. They go through changes, and we primarily have, for our intents and purposes now, two different types. We'll call them faceting, or the process we'll call faceting, and we'll call it rounding. When we get a lot of change of temperature over distance, we get faceting. When we don't get a lot of change of temperature over distance, we get rounding. That's really the only thing we need to remember here. Lots of change in temperature between the ground and the surface, faceting. Not much, rounding. Which type of grain we get here does affect our avalanche danger, and that's why we're thinking about it here. Our changes in the snowpack are what we'll call snow metamorphism. Metamorphism, simply a Greek word for change. Faceting, we take a crystal that falls from the sky, it lands on the ground, it starts to decompose, changes into a little more rounded grain, then through a process, it ends up as a facet. The facets here are what we'll call cups, like this. This here is an extreme form of faceting, and we'll call this depth hoar. It often forms at the back of the bottom of the snowpack. It doesn't have to be this extreme. It can just be pointy crystals that look like sugar, and it's often referred to as sugar snow. This type of process is promoted by cold air temperatures, shallow snowpack. Do you think this is, what do we have right now? Pretty much this. We're interested in these grains because they don't bond well to each other. They tend to be isolated from each other like grains of sugar, that type of thing there. Let's see if this will play for me. This is a clip of what happens. We have a rounded grain, it starts to grow these layers on it, and before long, at its extreme form, it forms this cup-shaped crystal that we'll call depth hoar. Depth hoar is the extreme form of faceting. Write that one down. You need to remember that at some point here. Extreme form of faceting, depth hoar. So that's the process for faceting. Oftentimes we'll look at it, we'll just see these growth lines on it underneath a hand lens. Again, here's our extreme form, these cool cup-shaped crystals. They're really pretty. Sometimes you can see them without a hand lens even. We can get faceting in the snowpack at different places. Remember, I said it depends upon that gradient. I simplified it by saying we get a certain gradient throughout the whole snowpack. I then qualified that and said that isn't quite reality. We'll often get changes at different places in the snowpack. Most typically, where we get the biggest temperature changes are at the bottom of the snowpack and the very top. Some of you folks might already have experienced what we'll call near surface faceting. If you've ridden it, skied, boarded, some people will call it loud powder. It sounds really abrasive underneath your board or your skis. It sounds like you're skiing on sand because you've got very sharp crystals that are rubbing on the base of your board or skis. That's near surface faceting. It can be great skiing. It'll ski like powder, but it isn't. It's a result of our gradient in the snowpack close to the surface, taking the grains through a change and faceting them. We'll come back to this at a certain point. As I said, facets tend to give us weak layers. Another point to write down, faceting equals weak layer. Imagine we've got a layer of these near surface facets. We've had great skiing, riding. On this stuff, it's skied like powder. Now we get a big storm coming in. Now we have this layer that used to be good skiing because it was a weak, sugary, sandy layer. Now that's buried. That gives us a buried weak layer that we need to be aware of. And we'll talk about this later in what we'll call a persistent weak layer, because these things are easy to form, but they don't want to go away very quickly. When we dig into the snowpack, we'll find facets. Oftentimes we can pull out a lens and look at them. More commonly, you can just put your hand in there and try and make a snowball. If you can't make a snowball, it's probably facets. So that's our first process, faceting due to temperature gradient. Our next one is rounding. Our grains, crystal decomposes and it forms a little round. That's promoted by warm air temperatures, a deep snowpack, and the grains might look like this. They try to stick to each other. They go through a process called necking, where they grow together and make these little necks there. Rounded grains, as opposed to faceted, tend to lead to a more stable snowpack. That's all we need to know there. So those are our two primary types. We can also call them persistent grains or non-persistent grains. Persistent grains, we talked about facets. We talked about depth hoar being the extreme form of faceting. These here are faceted grains. You can see these beautiful striations on them. We'll talk here now about surface hoar, which is another type of persistent grain. Surface hoar is the equivalent of frozen dew. How many people have seen surface hoar before out there? Beautiful little feathery crystals that grow on the surface. Anybody seen them? Yeah, Moody's waving. Not sure what Yannick's doing, he's grinning, but no, that could mean a lot of different things, couldn't it? So some of you might have seen it. This is surface hoar on the surface. It's called surface hoar because it grows at the surface. Depth hoar is called depth hoar because it forms at the bottom. We're going to come back to this point in a second. Surface hoar forms on the surface. It's not a problem for us at the surface. It's a problem when it gets buried, such as here. This is in Colorado. You can see these little crystals sticking up there. Now we've got new snow on top. We've got all these little things sticking up. They're weak. They want to fall over. They want to collapse. This is what we'll call a persistent grain type, and this could be what we'll call a persistent layer. The surface hoar here will form overnight, forms really fast. It's beautiful. We'll see it up at Mammoth fairly commonly. However, once it's buried, it takes a long time to go away, and that's why we call it persistent. We're not going to go into the whys, it's just because of energy balance there. So whenever we see surface hoar, we can go, oh, that's cool, that's pretty. But we also want to think of, well, that's cool, that's pretty. The forecast is saying we're going to get a storm coming in 2 hours. I wonder what's going to happen when this stuff gets buried. Get these bladed prismatic crystals. You can get really big ones. This is out in the anthracite range in Colorado. We've got different growth over different days. Each of one of these layers represents a night of growth. This stuff forms at night. So it's cool, beautiful stuff. Again, we don't have to go into the whys and everything of how it forms, but the things it takes to do it are cold nights, very little air movement, and a source of humidity. We often get this around Crowley Lake, where we've got the lake putting humidity into the air. It's a cold air sink, and we often get surface hoar formed there. So surface hoar is one type of persistent grain. It's often common in Colorado. Think back to our fatalities in Colorado. There's one reason right there. We get a lot of surface hoar formed that then gets buried. Same in Canada. For us here in the Sierra Nevada, particularly on the west side, one of our persistent grain types might be what we call grappel. And grappel is primarily the snow equivalent of hail. It tends to be a little styrofoam ball. And because they're a rounded ball, don't confuse these with rounded grains. These are falling from the sky. Rounded grains are forming in the snowpack. These grains that fall from the sky don't want to stick to each other. They act as a ball-bearing layer. So particularly on the west side, grappel's common. It takes a high degree of humidity to form it. And this photo is from the west side. Looking at avalanches in Canada, in Sweden, in Switzerland, surface hoar is one of the biggest contributors. Facets, any type of facet, a near surface one. Depth hoar, our extreme type of facet. So those three types there are things that we want to pay attention to, and we've just talked about those. And we're going to link this back later into our avalanche problem. Faceting and rounding are metamorphic processes. They're not good, they're not bad, they happen. We got to deal with them. So that's as much snow science as we need to go into. Does anybody have any questions? Are people clear on things here? Now's the time to ask. Put it in the chat. So I guess we got two choices here. My teaching is absolutely perfect and exemplary, or everybody's asleep. Could be either, couldn't it? Exemplary. Thank you, Gabrielle. You're done. You can leave now. The certificate's in the mail. So just one thing to clarify here, I said I was going to. Depth hoar forms at the bottom of the snowpack as an extreme form of faceting. Surface hoar forms at the surface as a result of changes at the surface. The two have that last hoar word, a common word, H-O-A-R. Don't misspell it. Depth hoar is not buried surface hoar. We call buried surface hoar buried surface hoar. Write that one down. That's going to be a question when we get in the field. So depth hoar is not buried surface hoar. Don't be confused here. Two different processes, but similar names. Now, it'd be ideal if there's a different name. There isn't. And yeah, these processes can create or reduce avalanche hazard. When we're out in the field, we're going to go ahead and we're going to make observations with our snowpack. Three different things we're going to look at here: snow cover, layers, and bonding. Sometimes we'll do formal observations. We'll dig into the snowpack, which gives us information, but a lot of the time we're going to go out and do informal observations. When we do formal work, we might take temperatures, we'll observe the snow grains, we'll make notes. It takes a lot of time to do all this stuff. And remember, our goal is to go out and ski and board and ride. The snow pits are important. They help us understand the snowpack, but they're not the answer. People think that when we go out there, we have to go ahead and dig a snow pit. Oftentimes they don't. I'll get information from other means. And when we dig a snow pit, it can give us data, but it's a snapshot. Now we've got a big picture, which is the terrain, and we've just punched one little hole in that, and we're getting a tiny little view of what's going on. It might be representative, it might not. Our ideal thing would be to dig a bunch of these little holes all over the place and get a big picture of what's going on under the surface. But if we do that, we're only going to get 100 feet from the parking lot, and we're not going to get out and ski and ride. So oftentimes we want to go ahead and get a bigger picture through informal information. But digging a pit will help us find hard over soft layers. And remember, hard over soft is type it in the chat. What type of an avalanche is a hard layer over a soft one? Slab, VJ, good job. Slab, okay. Slab avalanches relate to about 70% of recreational incidents. That's why we spend a lot of time looking for slabs. We can do a test, which enables us to put a number on something that we find to be unstable. However, it's very easy for us as humans to focus on, well, I got a 15. Well, I got a 20. Well, I got a 21. No, it's a number. It helps us make our decision, but it isn't the decision. We can do what we call a root block, which is a big block, and we put a real person on it. And this is all good data, and we might get a result like this, where a layer goes whoomph off. And here we have a hard layer on top of a thin, soft layer that slid off. The problem with doing our tests, as I said, is it's a snapshot. And this is what we call spatial variability. And this is the bane of our life. Now, things vary over snow. We'd like them not over distance. We'd like them not to, but they do. This is a test from Canada. It was on buried surface hoar, and the root block is scored from 1 to 7. 1 means it fails as soon as we start to dig it. 7 means it didn't fail at all. So let's say we dug a pit over here and we got a score of 6, which meant it failed after we jumped on it repeatedly. We might say, oh, I'm not seeing much instability in the snowpack. Over here, we do a pit and we get a 2, which means it failed as soon as the skier here, there, as soon as they stepped onto it. This is probably going to be a 6 if it fails there, if they jump on it. So over here, we dig this and we go, oh my God, check this out. So this is what we call spatial variability. This failed on surface hoar, and surface hoar is very erratic where it forms. And that's the problem with buried surface hoar. It's erratic. Other things are erratic too in where they form, such as our depth hoar, but particularly surface hoar. So we dig our pit and we take the data, we put it into our big picture there because of our variability. This is going to be a hard concept for people to get, but we will generally put our faith in the low numbers we get. We don't put our faith in the high numbers. We sort of say, no, wow, we got a low number, things are unstable. Over here, we say, I got a high number. That doesn't mean that there are not instabilities. It means I got a high number, I might have gotten lucky. Over here, no, we got the low number. You could say we got unlucky. So everybody wants to focus on doing a pit and getting a high number and saying, well, we're good to go. We're not. It's one piece of data. Good numbers, high scores, or one piece of data. Low numbers, we put a lot more faith in them. We'll talk about this a lot more when we're in the field. It's a bit of a hard concept for people to get. But we do spend a lot more time looking at informal data. What's the snow feeling like? Is it soft? Is it sticking? How deep is it? How variable? We'll use our probe here to probe with. Is it compacting? Originally, the snow was up to this level here on top of the tree. Now we've got a cone. As it packs down, air moves out of the snowpack and one grain bonds to another. Cracking. This is up at Minaret Vista last year. Tyler, one of our guides, put in his ski pole here and a crack shot out there. Something's going on in the snowpack. This might be our cue to stop, dig into the snowpack and see what's going on. Why did this crack? Why did it fail? By the time you get cracks like this, these should be sort of a slap over the head. Something's going on. Maybe I need to back off from what I was thinking. Maybe I'll dig into it and see. Now, is this restricted to one aspect, one slope angle? But probably I'm going to want to back off here. Now, nature's giving you a warning. Take it. We can go out and we can jump on little windrolls. We're going to talk about wind as we go along. but wind is a big architect of avalanches. We can just see how much does it take to break things off. As we do a kick turn, we can go up and we make a little V here. As she comes around, she could stop just here and jump and see what happens to this wedge. This is our mini root block. We didn't have to dig it. We made it as we went up. A quick on the fly. It doesn't take us any time. We can maybe go out on a small slope and jump on it. We've got to be careful. We've got to choose a small one. We don't want to put ourselves in danger here. But that might give us a representation of what's going on, bigger picture, all informal information. When we're out there in the field, we'll try and do what we call a shear test, where we cut a little block and we just pull on it and see if the layers move. And oftentimes we'll get that, get something to break off. Then we look at it and we think, oh, wow, that's interesting. Now, maybe I'll dig in and I'll do some of my quantified tests to get a number and just see how bad or how good, if I want to use those terms, how easy or how difficult it is a better term, to get that to break. I can do this as I'm sitting there waiting for my friends to catch up, really quick and easily. Now, is the snow wet or dry? This rollerball here would probably take you out if it hit you. So these are all questions we're asking. We come up with things that should get our attention. And we'll call these red flags. They're things that meet or exceed some parameters. We often think of a deep snowpack as being an unstable one. A snowpack of less than 1.5 meters should get our attention. A shallow snowpack is generally worse than a deep one. Most of our avalanches occur in the top meter of the snowpack. They can be deeper, but most are up high. Do we have weak grains? Okay, how about in the chat box? What's a weak grain? We talked to a facet. Yes, Daniel, thank you. Yes, a facet's a weak grain. Doesn't want to stick to each other. They want to stay independent. And variable. Is the snow thick, then thin, all over the place? When we look at the layers, we can do this by digging. Moody says hoar, depth hoar, yes. Strong over weak, we can feel that with our probe. We push in, it's hard, then woof, it collapses underneath it as we go through the hard layer. Maybe we're going from a hard layer to some facets. Snow likes to be below freezing. It doesn't like to be near or at freezing because it changes quickly. No, it just doesn't like that warm temperatures. Persistent grains. Okay, in the chat box, what's a persistent grain? Surface hoar, yes, when it's buried. Grapel, you got it there, Gabrielle, Ruby, and Chris. Yep, buried surface hoar, depth hoar, grapel, faceted grains. And then if we do a test, compression test, which is where we hit the shovel, and we'll do this in the field, less than 20. Roots block, less than 4, where we jump on it once. And anytime we get a smooth, clean failure, all of them in our tests, any of these sort of should give us a heads up and as a red flag. We might get one, we might get more. The more we get, the more attention we should give it. A lot of this might not make full sense now, but once we get out in the field, particularly these tests will. So that wraps up our snowpack red flag here. We've gone a little longer than I'd hoped, but does anybody have any questions? And we'll take a break. All right, we're all set to go here. It's a nice day for a ski tour out in the high Sierra. Don't believe all the advertising from Black Diamond that says it's all about the down. In the Sierra Nevada, it's all about the across. We've got the best ski touring imaginable, particularly when we get into spring. But we'll talk more about that later. Okay, so we talked about the snowpack previously. now we're going to go ahead and we're going to talk about weather. So weather, as we talked about originally, weather at the surface gives us our direct weather effects. And again, everything we see at the surface will one day be buried. That's what gives us an interface. The only exception might be the last snowfall of the season. We talked about precipitation, wind, temperature, solar radiation. We're going to delve into these in a little more depth now. Wind is the big architect of avalanches. Wind moves snow from one place to another and redistributes it. Where it gets redeposited, it can go ahead and create a stiffer, harder layer and a layer that's more compact. That is what gives us a slab, and that's what can be referred to as a wind slab as well. Wind can move snow up to 10 times more than it can fall from the sky. Here we have an example of a perfectly clear day, blue skies, snow is not falling from the sky. This is Wheeler Crest just outside my window. We can see that snow is being deposited in here. If you were in here, you would be in a snowstorm. It'd be windy and there'd be a lot of snow moving around. Right now, the wind here is forming wind slab conditions. When we put ourselves in there, that gives us a wind slab avalanche danger. So wind is the big architect here. And here we have an example of a wind slab. So precipitation. Remember asking ourselves questions about what's going on. Is it snowing? Is it raining? That's going to depend upon our prevailing temperature. And as we deal with climate change, we get more and more rain at higher and higher elevations. Sun. Again, we're getting warmer, sunnier days and much more solar input. Here we have what we call neve penitentes, or sun cups. They're very extreme, or these are extreme sun cups, very pointy, and the sun acts as a mini oven in between the crusts, in between the pillars there. When this is buried, no, it's probably not going to be much of a sliding layer, but different aspect or different types of solar input are going to give us sun crusts, and those can be layers that will get avalanches forming on. Temperature. Sun, let's say solar radiation and temperature are not the same thing. Temperature is the result of solar radiation interacting often with a medium. It heats up the air, it heats up the ground, and increases the temperature. We've all been out there on a sunny day when we're cold and wearing a lot of clothing. We can go from in the sun, where we're absorbing solar radiation ourselves, into the shade, where we've got to put more clothing on because it's cold. So temperature, we'll get warm temperatures at night, even though we're not getting solar input. So temperature and radiation are two different things. At the surface, temperature can have a similar effect to sun, and it can cause the surface layers to melt and then later refreeze. Now we can get information on what's going on before we step out of the house. We can go ahead and we can pull up forecast. We've got a lot of different resources here. I tend to use the NOAA forecast. Other people will develop what they want to use. For people who haven't done it before, you can go ahead and use Mammoth Ski Patrol site. Just put in a search bar, Mammoth Ski Patrol. This is going to give you temperatures at Main Lodge at 88-90 feet, and at the top at 11,053. So we'll often see, what's going on there in real time. And that's definitely a value there. So use that resource. I use it all the time for Mammoth area. In terms of weather, we're going to ask ourselves, has it snowed recently? Back here, we've got our forecast. When we look out the window, we've essentially got our nowcast, or out the window forecast. What's going on right now, which might be the same as Mammoth, or it might be the same as National Weather Service, but it might not be as well. Weather is local. When we look outside, we're asking ourselves, has it been windy in the past? And is it still windy? Is snow getting moved around by that avalanche, by that wind? And is that creating new avalanche hazard? Is the wind picking up snow from one place, putting it another, creating that stiffer slab? The wind will tend to push one grain against another, giving a mechanical bond there. And this is going to happen at the surface. This is different to rounding. Rounding effectively is a chemical process, if you want to call it that, of bonding one grain to another. Wind slabs are formed by a mechanical process of pushing one grain against another. California, most of our storms come from the west, out there off the Pacific Ocean. Our Sierra Nevada runs northwest, southeast. Now, we often think of the Sierra Nevada as being a north-south range. It isn't. It's inclined. We can look at our forecasts and we get an idea of what the wind is, which might help give us an idea of where and how much slab avalanches are being created. However, our wind is always affected by local terrain, and we have to keep that in mind all the time. So looking at these weather maps here, this shows sort of the difference between wind at different elevations. This here is at surface, I think. And when we look at this, we're just down, we'll say Bishop, we're in here. The wind is a number of different directions there. As we move up in elevation, the flow changes. It's no longer affected by local weather conditions. Now it's primarily coming out of the southwest. Then when we get up, this is about 2,000 meters here. When we get up high and into the jet stream at about 11,000 or 11 kilometers, 11 here, whoops, let me back up. Here now the flow has shifted all the way to more the west and very consistent. So wind is going to vary with elevation. We have to keep that in mind. Wind is going to vary depending upon the terrain, and we have to keep that in mind as well. This is up at about 40,000 feet here. When we look at terrain, we're always thinking about wind direction, because wind will form slabs. Slabs are related to 70% of recreational accidents. We're trying to assess where that might happen. One of our biggest indicators of wind are cornices. Cornices form pointing downwind. Cornices are the overhanging lips of snow along a ridgeline. The wind comes over the top at vortexes and it scours and deposits, creating these overhanging lips here. So in this photo, the wind has been blowing right to left. And as we go along, we're going to be asking ourselves, and I'm going to be asking you, where has the wind been blowing from in this photo? Cornices are one big indicator. Wind will move from the right here, come over the top, create this cornice. As wind speed drops down here in this area, one grain is mechanically bonded to another, and That's what forms our wind slabs. Wind slabs will form on the downwind side of a ridge. And we're going to get into this more as we go along when we talk about avalanche formation. But keep that in mind for later. We'll also look when we're out there for these little arrows behind objects, trees, rocks, vegetation. Again, these form downwind. So the wind has been moving right to left. It slows down behind an object and deposits in there. As I said, the wind can move snow up to 10 times the rate it can fall from the sky. Again, a clear sky. We've got a cornice along the top here. Wind is blowing behind forward. Right now, it's creating wind slabs in these areas at the tops of these gullies. As skiers, boarders, maybe climbers, we want to maybe ski where most of the snow is, but that's also where most of the danger is. Like the snowpack, we're going to go ahead and identify some red flags, things that get our attention. We think about what the precipitation is. Is it rain or dense snow? How fast is it falling? 2.5 centimeters, an inch an hour. That's our rule of thumb there. That much snow for an hour doesn't really matter. So we also want duration of that rate. So 12 hours or more, which is going to give us close to 30 centimeters of snow. So about a foot over 12 hours should get our attention. Wind, we don't have to put a number on it. Is it moving snow? Is it putting snow where we're heading? As we talked about with snowpack, temperatures anywhere round about zero. Freezing temperature, not freezing or rapid changes. Snow does not like rapid changes. Solar radiation, strong and for long periods. You know, the sun coming out from behind a cloud, no, it doesn't matter. The sun in a clear sky all day does matter, because it warms up that snowpack, it brings it up to our 0 degree temperature. So those are things we're thinking about with weather. Along with weather, we'll have what we call, or we'll talk about what we call snowpack climates. There's 3 for us in the Western US: maritime, intermountain, continental. A maritime climate tends to be typified by a deep snowpack, warm temperatures. What type of grain do you think will form in this environment? There was 2. One started with F, one started with R. Put it in the type box there for me, in the chat box. Rounding, says Nicholas. Yes, indeed. Is rounding in our snowpack? So does Ruby. Is rounding in our snowpack a good thing in terms of avalanche stability, or a bad thing? Put it in the box for me. Good, says Kate. Yes. So rounding tends to lead towards more stability because grains are chemically bonding to each other. Okay, now maritime there. Oh, this is, sorry, maritime. It's Mammoth here, a couple of years ago. Now we've got a deep snowpack, warm temperatures, relatively thick uniform layers. Avalanche danger kicks up fast, then generally drops off fast. Continental, cold snowpack, cold temperatures. What are we going to get here? The F word or the R word? Who's kind of? Yana says Facet. Yep. So is Nicholas. Yep. Okay. In terms of our avalanche danger, is that going to lead to a more stable snowpack or potentially a more unstable snowpack? Yep. Yannick says high danger, unstable. Moody put in stable. No, it's going to be more of an unstable. Kate put in unstable. So we've got more danger in a continental snowpack. We've got shallow temperature, cold temperatures, shallow snowpack, variable shallow layering. It's easy for us to blunder from one place to another. Avalanche danger is slow, is quick to rise, slow to fall. Intermountain is basically right in between the two, as we'd expect. We can have a snowpack that sometimes is shallow, other times deep, often variable. The Wasatch is a typical example of an intermountain snowpack. On the east side of the Sierra Nevada here, we have different canyons that some have more of a continental aspect, some have more of an intermountain aspect. Not continental, sorry, maritime. And others have more of a intermountain. Let's relate that back now to what we talked about with our accident rate. What states seem to have the highest number of accidents given their relatively small populations? Put that in the chat box there. Colorado, Utah, okay. What type of snowpack do you think they have? Maritime, continental, intermountain. Continental, yep. Moody says intermountain. Some of them are. It's generally Montana, Wyoming, Idaho tend to be more of a continental snowpack. Continental snowpacks tend to catch more people in avalanches than maritime such as us here. All right, so that is our presentation on weather. Does anybody have any questions there? We're back to our triangle here. We've talked about snowpack, weather, and now let's talk about terrain. So terrain, let's see, question. Sun cup's considered a strong layer, says Yannick. They'll bond the next layer of snow fairly well to them because they have a lot of what we call terrain roughness. We'll talk about that as part of this terrain presentation. Terrain roughness helps glue one layer to another. But once those sun cups or that terrain are covered, then we're back to sort of square one with none of that being available to bond the layers. And VJ is asking, does solar radiation have non-temperature dependent effects on the snowpack? Solar radiation is always going to increase, or presence will increase temperature, and lack of it will decrease temperature. We'll get into this in a little bit here, I think, Vijay, and we'll talk about lack of solar radiation as having an effect upon the snowpack that then moves into an increased potential avalanche danger. So hold that thought for a moment, and if it doesn't make sense to you as we go through, we'll cover it then. So terrain. Now, we can't control a lot of things, but we can control the terrain we go into. We can control how we go into it. And that's why we want to focus on this. We're going to talk a little bit here about recognizing avalanche terrain. Now, what does it look like? If we can recognize our terrain, we can then go ahead and decide how to choose more aggressive or more conservative terrain. And this is one of the more important skills you can have is in terms of recognizing avalanche terrain. Here we have the Sherwins out of Mammoth. And this is big avalanche terrain. And it's fairly complex terrain as well. Over here, we have a large avalanche chute. We can see large trees, small trees, large trees. This here and down here is the main avalanche chute on the Sherwins. We've got another one feeding into it here, feeding in over here on that side. Over here, we've got another avalanche chute there, a number of feeders coming into it, and another chute that comes down a little bit out of sight behind there. All of this across in this area used to be covered in big trees. And President's Weekend, 1986, I was working at Rock Creek then. We got 16 feet of snow over 4 days. And that's when all these trees here got cleaned out. All the trees ended up down the bottom in Mammoth Meadow, and Mammoth had firewood for years after that. That was a good big storm. We've had bigger years, but that was the last giant storm that we really had. So this is complex avalanche terrain. This area is skied a fair bit, but it is also complex and it leads to accidents. And if we're there during the field days, we'll talk about it then. When we look at terrain, there's two crucial things we want to look at. We want to look at the slope angle and we want to look at the aspect there. So slope angle. Most avalanches happen between 30 and 45 degrees. Below that is too shallow to slide. The lowest angle I know of for an avalanche was 12 degrees. That happened on a Japanese volcano where there was an awful lot of people walking out of it, and basically their weight overwhelmed the cohesiveness of the snow. Above that, we really don't get it accumulating too much. The thing is that oftentimes as backcountry users, to get to over 45 degrees, we've got to go through the 30 to 45 degree range, unless you're jumping in from the top. But you'll certainly get avalanches up here. We don't get the big avalanches in the above 45 degree range, but we'll get a lot of smaller ones. But because we're in far steeper extreme terrain, it doesn't take much of an avalanche to be a problem for us. So 30 to 45 degree range there is where we're most concerned. The thing is, as skiers and riders, this is the range that we will probably have the most fun in. There's our catch-22. There's a lot of ways we can estimate slope angle. And web-based tools work a lot. Will work fairly well. We can shade the angles according to the map here. And this is from CalTopo, Hill Map. There's a number of different ones, Gaia. They all give the ability to get slope shading, and that's a very useful tool. We can also go ahead when we're out there, use an inclinometer, and I'd recommend that people carry an inclinometer with them. On our web-based tools, that doesn't mean that within these contours, there isn't going to be a slightly steeper angle. No, it's an overall average of things here between the contours. This here will probably give us a better idea of what we're dealing with right there and then. Looking at Mammoth Mountain, I'm sure a number of people have skied a number of these runs. On any avalanche path, we'll talk about the starting angle, which is where an avalanche initiates, and the path, which is where it travels. And these are some of the angles in Mammoth. Most advanced ski runs are probably going to be 30 degrees. You say it quickly, 30 degrees doesn't sound like much. Doubled black diamonds are probably going to be about 35 degrees. Now, 40 degrees feels pretty damn steep when you're at the top of it looking down. Now, if somebody says they ski 50 degrees on a regular basis, they're either a really good skier or they're lying. 50 degrees is got a huge pucker factor to it. And consistent 50 degrees is not something I want to go anywhere near. Now, again, most of us are going to have fun around about 30 to 35 degrees. Prime avalanche conditions right there. When we're looking at terrain, we're thinking about it in relation to its aspect to wind. This is our second factor, angle, aspect. Aspect in relation to wind, because wind forms slabs. Slabs give us a major avalanche problem. We'll have two types of aspect in relation to wind. First one we'll call lee loading or top loading. The wind is moving from left to right here, from there to there. It picks up snow on this side, it moves it across and deposits it onto our lee slope. Right here is where we might get a cornice formed. Cornices form dependent upon the angle below them. We need a certain angle below them to form a cornice. If it's too shallow, we don't get that cornice. So this is lee loading, loading onto a lee slope, loading at the top of maybe a ridge. Or we could get cross loading. This is when this wind blows across a slope. Now we have a whole series of little mini lees. The lee, it's a sheltered area behind the ridge there. Here we might just get one wind slab formed at the top of this slope. Remember, wind forms wind slabs. Here we might get a series of wind slabs all the way across behind each little ridge line. So I've said before that cornices indicate wind direction. They're going to be one of our clues that we use. So looking at this photo here, where do you think the wind has been blowing? Left to right or right to left? Type it in for me. Look for your clues. Okay, Yannick says left to right. Left to right, says Brielle. Why are you all saying that? What's your clue? Goman says, what's our clue here we're looking at? Why do you guys say that? Better justify it. Scouring on the left side. Snow loaded on the right side. Left sides are empty, yes. Yes, but there's something else I'm looking for here. Look closely. Cornice, says Brielle. Yes, that's my main clue. No, yes, we're right that wind is that there's snow missing here, but what else could that be a result of? It could be sun, says Alex. Yes, exactly. Yannick says warming, but direct result of sun. So our clue, though, is the cornice line along here. It's been picking it up on the left side, depositing on the right, picking it up on the left, depositing on the right. So again, we're looking for that cornice clue. So we've got a series of windward lee, windward lee, windward probably around the corner. Okay. Here we have, this is a slide just outside of ski area in Colorado. Ski area has put a charge in here. This here is what we call a pillow of snow. It's fractured all the way around and it's about to release and slide. Looking for our clues, where has the wind been blowing from in this photo? Across the mountain, yes, but which direction? Right to left or left to right? Paul says left to right. Yep. So we've got little piles of snow behind objects. We've got deposition there, scouring there. It might have been coming more across the slope, bottom to top, says Gabrielle. Yep, probably. So it's been removing it up there and blowing across slope. It's deposited a pillow in here. Our problem is, when we look at this, where do we want to ski and ride? It's not over here. It's right here. And no, there's a reason why it looks good, because snow's been deposited there. So again, it's that catch-22. We want to go where the snow is to ski and ride, but that's also potentially where the most danger exists. Therefore, we have to make an assessment, is today the day to go in there? Is that today not the day? Ski Patrol obviously knew something was going on, which is why they put a charge in there. So, yep, wind across the slope. All right, Red Mountain, just down the road out of Tom's place. Where has the wind been blowing from in this picture? The west, okay? Where's west? Left to right, okay, over the mountain, says Chris, and Yannick, towards the camera, says Brielle. Top loading, yep, good job. From the back to the front, top loading, yep. So we've got cornice up along the top here. We do there, so it's been blowing behind forward, depositing there. We've got a cornice along the ridge line here, so it's also been blowing left to right. We've got a fracture line there. So that's where our wind slab was formed and created. So yes, we've got top loading and we've got cross loading. We've got little fracture lines in there. It's scoured there, deposited there. So a lot going on in this photo. So snow varies over terrain. Here we've got potentially scouring as the wind blows across, and we've got deposition there. We've got deposition as the wind blows behind forward, giving us top loading. Again, all these gullies here are things that we look as if we'd like, or look like we'd like to ski or ride them. We'll talk more about where we're going to choose to ski and ride, but in these cases, maybe we're better to take the high line on things rather than the most obvious chute there. Aspect. Still in, no, we're talking about aspect. We've got aspect in relation to sun. Sun is a good thing and a bad thing, which gets back to the question earlier that somebody had. It stabilizes and it destabilizes. When we get too much of it, it decreases stability and increases instability, particularly on slopes that face it. On the other hand, a little bit of it helps warm the snow, gives us warm air temperature, which leads towards our rounding, which will help promote stability. The absence of it, we'll talk about that in a moment. Here we have, where are we? Around Thousand Island Lake somewhere. Solar input in the sun, in the spring. We're getting a lot of avalanches forming here. We'll talk about the types of avalanche as we go along, but this is what we call a loose avalanche. Thinking back to what we talked about earlier, we've got an unstable layer or a soft layer on top of a hard one. And that's what gives rise to these. So this is as the sun is hitting the slope. The flip side of this is where we get a lack of solar input. We have cold temperatures here, a shallow snowpack. Think back, what type of grain do you think is going to persist on this aspect here? The F word or the R word? Type it in. Faceted, yep, I'm getting the F word from a lot of people. So facets are going to persist because of that lack of sun. So again, a little bit of sun is good to promote stability. Too much of it is a bad thing. There's plenty of things in life like that, I guess. So let's just talk about parts of an avalanche terrain. I talked about these briefly before. We've got the start zone, we've got the track where it accelerates, we've got the run out zone. This is in Canada. The little mounds at the bottom are what highway departments put to try and dissipate it before it hits the highway. Pointed out with Sherwin there, out of Mammoth, we're looking for vegetation clues. Lack of vegetation could well be an avalanche path. And but often below tree line gives us a pretty good clue as to where avalanches run. We can look at vegetation up close. This here is what we call flagging. An avalanche ran up to this level here. It stripped off trees on the uphill side there. Bent over these ones there, strips them off there. In the snow, we might see debris. So those are all clues that we're in avalanche terrain or we're in the run out area. So we're constantly, as I said, evaluating terrain. I mentioned anchoring earlier, surface roughness. How well do you think snow is going to stick to a nice Tuolumne dome such as this one? Probably not very well. So we have very little surface roughness here. And this will also relate to a type of avalanche that we'll talk about later, called a glide avalanche. Where we have a lot of surface roughness, early season snow is going to stick pretty well to this. But once we get it covered, then it becomes more and more irrelevant. So early season, like right now, surface roughness is an important factor. By the time we get to late February, March, it's probably less so, assuming we get loves the snow. When we're also looking at terrain, we're thinking about trigger points, which are places where an avalanche can originate and initiate. Trees and shallow rocks can be a trigger point. Let's think. Here is a tricky question for people. Here we have a rock that's poking through the snow. Out there, we have deep snow. In here, we have shallow snow. Remember, our ground is at 0 degrees and our air is whatever. What type of snow do you think, or type of grain do you think we might get formed around this rock, and why? See if anybody can figure this one out. Put it in the chat box. Let's go with the type of snow we might get around the rock first. Type of grain. Who's going to go for it? Think about our temperature gradients. Do we have a lot of change of temperature over distance here or there? Remember, our ground is at 0, our air is at whatever. Rounding because the warm is not quite, Kate. We'll come back to it. So, no, who's going to use exam technique here? If Kate wasn't quite right, what's the alternative? Could it possibly be the F word? Because Yannick says, well, it's cold and shallow. Yes, it's shallower here. So we get more, remember, 0 there on the rock, also 0 on the ground, whatever it is up in the air. So we get more change of temperature right here than we do there. So we're more likely to get facets around the rock. Facets are weaker, so the rocks can act as a trigger point. Does that make sense to you, Kate? Is it, no, ground is not necessarily warmer than the air. Okay. All right, so that's why we can get faceting around rocks. That's why rocks can be trigger points. Trees act as dots in the dotted line, basically. So here we see fracturing around these rocks. This is where we can potentially get facets formed. So there we've got a rock there. This avalanche could have initiated at this rock. Shallow, it's poking up. Far more than here. We're more likely to get faceting around here than we are over here. Convex rolls. This is another place we can trigger something in terms of our terrain. At the top, we've got gravity pulling things apart. At the bottom, we're getting it compressing. Both of those areas are areas of increased stress. At the top, it's trying to pull it downhill. It's under tension. We blunder in there, we can be the extra little bit of load that makes it fracture. So that's where we get convexity stress there. However, we also get stress down here. This one's a little bit harder to realize. You think compressing is good, but it's still a stress. And that stress there is often gives rise to what we call remote triggering. Remote triggering is kind of a scary concept. So whenever we're out there, as we're skiing along, we're putting stress on the surface. We have what we call a stress bulb. Imagine a little onion-shaped bulb underneath our skis, traveling along as we go. Let's say that we have a weak layer within the snowpack. Let's just say it's our little surface hoar crystals sticking up. They've been buried. We've just got some new powder. It's fallen on top of that surface hoar. We're going along with our stress bulb, and maybe we go to an area of shallower snow. Our stress bulb goes down, it intersects our crystals, they all go collapse down. As they collapse, they expel air from the snowpack. As that air moves out, it makes a whoomphing sound. Has anybody heard that whoomphing out there? As you travel along on your skis or your board or split board, you might just hear boom. You might feel it vibrate in your feet. It can be a pretty scary thing. It should get your attention. It means something has failed. Now, along with that air going out, we also get a shock wave. Should that shock wave, it'll travel along that, all the crystals might just all fall over. It intersects our area of tension. There, we add more stress to that area that's already under stress, and that's enough to make that fail at that convex rollover. That in itself is not a problem, because we're up here on the flat. Let's imagine now that we're down here at the bottom, and we do the same thing. We collapse that layer, that shock wave travels up, it intersects this, and suddenly we've got stuff coming down on top of us, not below us. That's where remote triggering comes in, and it's a little bit of a scary concept. Probably more in Colorado than it is here. This is remote triggering in Alaska. There's a fairly small avalanche. I came up from the right here. We pulled onto a flat spot. This is the backside of Mount Dickey in the Ruth Gorge. I pulled up here. There was a whoomph, and a moment later, this broke off. The wind had probably been blowing from behind forward, created a wind slab here. Pretty small, maybe 20 feet across, less. However, we've got a crevasse right there. So a small avalanche could put me in big danger from this crevasse here. We were climbing. I triggered this. We had a big, broad plateau. I could put people out on the left. We could go up the slope over here one by one. It was slightly less steep. Probably the same conditions existed here as existed here, but we didn't have a crevasse below us. So given those factors, I believe that we were safe to keep going on up, or let's not say safe. I thought the risk was justified enough to keep going up here. If any one of those factors hadn't been there, then we wouldn't have done it. So that was mitigating the risk, even though the risk existed. The crevasse over here is what we would call a terrain trap. And a terrain trap is something that will increase the consequences if we're caught. Here is the narrow canyon and going to the ice climbing area on Lee Vining. It's a narrow gully. Terrain traps, gullies and drainages. Now we have a small amount of snow coming down, but it all funnels into one area. So it's exaggerating that. So that's one place we can get caught. Road cuts. We're at the bottom. We have a steep slope above us. People often think that a road is the safe way to go. Yes, it might be in the summer, but in the winter, we have to consider what there is above us. Cliffs. A small avalanche here can take us over one of these cliffs. This is on Rainier. Climbing group, but they still have danger above them. And they all rope together. A small avalanche as you traverse across can be enough to knock you off. Drainages. If you get pushed into a creek, you're in another type of terrain trap. Trees. You can get pushed up against a tree, then all the snow piles up on top of you. We like to think that trees are safe. They're not. Remember, they act as a dotted line. That can be a trigger point. They also give us a terrain trap. The trees give us a nice, warm, fuzzy feeling. People say, well, if something happens, I can grab the tree. Yeah, it's nice, but it's probably not going to happen. So terrain traps, trees, avalanches will occur in trees. If the trees are dense enough that we can't ski through them or ride through them, an avalanche probably can't move through them either. Cornices, another type of terrain trap. Here we have a crack and somebody's already stepped over it. Every cornice has its day. Every cornice will fall off. You just want to be there, don't want to be there when it happens. No, we're asking ourselves, are we in the run out? This here is Tobacco Flat, accessing there. People who know the Mammoth area, that is Convict Lake, just there. You can come up this drainage. A number of years ago, a couple of guys went into Mammoth Mountaineering and talked to friend John there. Asked John where to go. John said, well, you know, we've got new snow. I'd probably stay down low in the trees. One of them said, well, that sounds good. We don't want to happen today. What happened yesterday? Which, of course, John asked, what happened yesterday? They came up the gully here. They were in the low angle at the bottom. Remember our slope angle, 30 to 45 degrees. They decided we're not in 30 to 45 degrees. We're not in avalanche terrain. We won't turn on our beacons. This here is the terrain that sits above that gully there. I don't know whether they remote triggered or whether it was natural, but as they came up here, an avalanche came down from above. It buried one guy pretty much to his shoulders and one guy to his legs. The guy buried to his legs was able to access his pack, dig himself out, dig his buddy out. They failed to recognize that they were in avalanche terrain, even though they were on a 10 to 15 degree slope. How could they have avoided this terrain trap as they came up this area here? How could they have used the terrain, stayed to the side? Which side? Upper ridge? Yep, all that's true. Yep. They could have come just up it 2.5 times. I don't know that there's a number, but they could have just stayed on this side over here and pulled up onto the ridgeline. No, we will go out, we will go into terrain traps, but we want to choose the right time and we want to minimize our exposure in them. If we were skiing the gully here, maybe we'd ski down it, we pull out to the side and ski it one at a time. And we'll talk about that in terms of our terrain techniques. So we'll go ahead and we'll just avoid terrain when we have to. So down here, people are down in the gully, in the flat. They're well away from slopes on either side there. This is heading to South Fork Pass in Big Pine Creek. So red flags for us. Slope angle 30 to 45. Wind loading, cross or top. Are there trigger points? Are there convexities? Are there concavities where we can remote trigger? We've got to combine our terrain with our snowpack and our weather. Are there terrain traps on our path? What's the relation to sun? Probably doesn't matter in early winter, matters a lot more in late winter when we're getting sun hitting the slopes. So that concludes our terrain presentation. Remember, we can choose the terrain we go into. It's our big choice, and the answer to most of our questions is probably going to be terrain. So any questions there, ladies and gentlemen, and if not, we'll take a break.